Okay, so welcome back to this next video in which we are discussing subspaces of vector spaces. Okay, so we've discussed now that a subset of a vector space will indeed be a subspace if it obeys these three criteria here. Okay, so if you want to make sure that a subset is a subspace, all you have to do is check these three criteria are obeyed by the subset. Okay, those will do. Okay, if you've checked these three, then it will be a subspace. Okay, so I'll just remind you of what these three criteria are because we're about to use them. Okay, so it needs to be closed under addition, so if you take any two elements of the subset and add them together with the inherited addition law that's on that subset from the large vector space capital V, you must get another element of the subset capital W back again. Okay, it must be closed under scalar multiplication, so if you take any element of the field, little c, and any vector in the subset, little w, and scalar multiply the vector w by the element of the field c, that answer must be an element of the subset w as well. And finally, the zero vector from the larger vector space capital V must also be an element of the subset capital W. Okay, so in this final video then, what we're going to do is we're going to look at examples of subspaces. So firstly, what I want to discuss is the two trivial subspaces. Okay, there are two subspaces that are always subspaces. They're always there, no matter what vector space you have, no matter what field it's over. Okay, and those are the entire set itself, so the entire vector space. That's a very boring one. Slightly more interesting is the zero subspace, so we'll go over those in a moment. And then the other thing I want to do is go to the most intuitive vector space that we have, which is R3, and have a look at what subspaces look like in R3. So I want to characterize what subspaces of R3 actually look like, using our intuitive picture of what R3 looks like and what addition and scalar multiplication mean in R3. Okay, right. So firstly then, let's just discuss these two trivial subspaces that are always there. So we have some arbitrary vector space capital V here, okay, over some arbitrary field capital F. Okay, and I want to tell you about two subspaces that are always there. Okay, so one of them is just the entire set V itself. Okay, so if you let W equal V, now V by definition is a subset of itself. It's not a proper subset, but it is a subset. Okay, so you can let W equal the entire set capital V. Okay, then when you restrict the composition laws down, there's no restriction to do whatsoever. You just keep the exact same addition law and the exact same scalar multiplication law. Okay, and of course we know that that subset with those composition laws on will indeed be a vector space, so indeed it is a subspace. So it's one of the trivial subspaces, but it is always a subspace. Okay. The other trivial one that's slightly more interesting than that one is the one that just contains the zero vector, so it's a set that contains one thing. So in this case, W will equal the set that just contains one vector from the vector space capital V, and that one vector will be the zero vector. Okay, 0 here, the additive identity within our vector space. Okay, so why is that going to be a subspace? Well, we know that if we want to check that a subset is a subspace, we only have three criteria to check. Okay, we need to make sure it's closed under addition. Okay, so if I take any two vectors from my subset capital W, it has to be the case that if I add them together, I get another element in that subset capital W. Well, there's only one vector in here, so the only possible addition I can do is adding 0 to 0. But of course, when I add the 0 vector to itself, I get the 0 vector back again, because the additive identity plus the additive identity is the additive identity. It does nothing. Okay, so indeed, we do have closure under composition. The only addition that I can do here is addition of 0 with itself, and that gives us 0 back again. So it's closed under addition. Next, I need to make sure that it's closed under scalar multiplication. So I need to make sure that if I take any element of the field, so C is an element of the field, I need to make sure that if I multiply C by this 0 vector, Okay, scalar multiply C by the zero vector, that I end up with something back in W. Okay, well this is something we haven't actually seen before. What happens if you take an element of the field and you scalar multiply it with the zero vector? Well, the intuitive answer is correct, but we need to see why it's correct. Okay, so the answer is you get the zero vector back again for absolutely any C that you can possibly use in the field. So why is that going to be the case then? Okay, well we can prove it using part 1 of distributivity that scalar multiplication must obey. Okay, so going back up to our axioms of scalar multiplication then, we have part 1 of distributivity here, saying that C times V plus V bar must equal C times V plus C times V bar. So the instant we insist that this is true for any C is an element of the field and any V and V bar are elements of the vector space, it instantly becomes true that if you take any element of the field and use it to scalar multiply the zero vector, the answer must just be the zero vector. And let me explain why. So we will quite simply let V bar here equals 0 bar, okay? Or rather, sorry, not 0 bar, 0, okay, the zero vector. So we'll take C times V plus the zero vector here. So this 0 is the zero vector. Okay, now if we apply this distributive law here, what do we get? This must equal C times V plus C times 0. And let me stress, C and V are arbitrary elements of the field and vector space respectively. They can be whatever you like. I've not set any conditions on those. Okay? But if we look at this side more, the left-hand side here, we can work this out. We can say, okay, V plus the zero vector is just going to equal V again, because the zero vector, when you add that to any other vector in the vector space, it just gives you the other vector back again, because it's the additive identity of addition in the vector space. So this answer will just be C times V here. So we've got that C times V is equal to C times V plus C times 0. So what we can now do is add the additive inverse of C times V onto both sides of this. Okay, so we'll add negative CV onto both sides, and what that will do is get rid of the CV's on both sides. So we'll get the zero vector on this side. We would get the zero vector plus C times 0, but that's obviously just equal to C times 0. So this becomes C times 0, the zero vector, is just equal to the zero vector. And remember, I set no condition on what C was equal to. This is true no matter what element of the field you're using, little c. Okay, so any element of the field scalar multiplied by the zero vector gives the zero vector back again. Okay, so that is why that is true, because if I take any element of the field, multiply it by the zero vector, I get the zero vector back again, so indeed it is closed under scalar multiplication. Indeed, my composition laws on this subset look extremely boring. Here is my addition composition law. I've just got one vector, and 0 plus 0 is 0, so there's my addition composition law. And my multiplication composition law, or rather scalar multiplication, what I'll have is 0 is the only vector up here. I'll have all of the elements of the field, the potentially infinite field here, okay, down here, but the answers in this composition table of scalar multiplication here are going to be extremely boring. It's just going to be a great big column of 0 vectors, okay, on and on it will go, a great big column of 0, 0, 0, 0, 0, 0 in every single entry. Okay, and that is why this is indeed closed under scalar multiplication. Okay, finally, axiom number 3, or property number 3, criterion number 3 even, okay, we need to make sure that the zero vector is in W, and of course the zero vector is in W. That's the only element that's in W, okay, so that one is obeyed as well, and we know that as soon as it obeys all of those 3 criteria, it will indeed be a subspace. So that is always a subspace that you can have of any vector space over any field, okay, and it's called, I'll just write this down, it's called the zero subspace. Okay, so these 2 subspaces that are always there for any vector space over any field, capital F, are called the 2 trivial subspaces because they're not that important. Okay, Any subspace that is not one of these two, is not a trivial subspace, is called a proper subspace, a more interesting subspace. Okay, and what we're now going to do is go to our nice intuitive vector space R3 and have a look at what subspaces actually look like in R3, because it's very easy to completely characterize what subspaces look like in R3. Okay, so our example then now, and I'll try and squeeze it in down here, but I'll probably fail, okay, is going to be in R3. Okay, right, so let me just remind you of what R3 is. So R3, the formal abstract definition, the real definition of what R3 is that it's a set containing all triplets of real numbers. So we'll have x1, x2, all the way up to x3, where all of these elements, all of these components, xi, are elements of the real numbers. Okay, so we have these row vectors, as they're called, which are triplets of real numbers. Okay, and that's what this is as a set. So you've got all triplets of real numbers. So you let this one vary over all real numbers. For every single thing that you can put there, you put every possible real number here, and then every possible real number here. You collect every possible combination that you can possibly dream up into this set, and that's what this R3 is as a set. Then what we're going to do is define an addition law and a scalar multiplication law on top of this, okay, and the addition law works like this. So if I have one vector, x1, x2, x3 here, and I want to add that to another vector which I'll call x1 bar, x2 bar, x3 bar, the way you do it is just component-wise. So the answer will be x1 plus x1 bar, okay, where x1 and x1 bar are both elements of the field, and we're adding them together in the field. Okay, so you add the components together in the field of real numbers. Okay, component number 2 will be x2 plus x2 bar, again, where you just add these two real numbers in the field of real numbers. And then x3 plus x3 bar here, again, where the addition is done in the field of real numbers. So that's how we can define addition of two vectors together in this set. And then scalar multiplication, if we've got some real number c and we want to multiply it by the vector x1, x2, x3, the answer will just be multiply all of these components here by the real number c. So multiply c and x1 together in the real numbers, c and x2, and c and x3 here. So that will be how you define scalar multiplication. And this set here of all triplets of real numbers with this addition law and this scalar multiplication law on it actually does obey the axioms of a vector space. So this is a vector space. Okay, right, but of course that's the abstract definition of R3, and that's the true definition of R3. That's exactly what it actually is, this abstract mathematical structure. However, the reason we love this vector space so much is not for its abstract mathematical definition. This is incredibly complicated because this field is horrendous, okay? But the reason we love this is because this just happens to be visualizable, okay? There is an intuitive picture that humans have great intuition for, which we can associate with this incredibly abstract mathematical structure. Okay, so let me show this here. So here is our intuitive picture. We have a three-dimensional grid here, and to every single one of these vectors here, we can associate a point in this great big grid, basically. And then we can think of the actual vector as being the position vector to that point. Okay, the arrow that connects the origin of this grid to that point. Okay, so what you quite simply do is if you want to associate this vector x1, x2, x3 to a position vector in this grid, an arrow in this grid, you let the x-coordinate be x1, the y-coordinate be x2, and the z-coordinate be x3. Okay, so let's say this is x1 here, this is x2 here, and this is x3 here, and then what we'll have is an arrow to that point up here, and then that arrow is the thing that we are associating with this vector here. Okay, right. And why is this so wonderful? Well, the reason this is so wonderful is that in this picture there is an intuitive notion of what it means to add these two vectors together and scalar multiply a vector by an element of the field. Okay, so if you've got two vectors, Okay, let's have the green vector there, and then we'll have the pink vector here. And you add them together in this abstract structure here. You add these two things abstractly together. What that corresponds to doing in the picture, and this is truly beautiful, it just means put the two end to end. So take this pink one and put it end to end with the green one, and then take the new point that you get up there, take the arrow that goes to that new point, the net position vector if you like. Okay, and that's going to be your answer now. So in orange here, there is our answer to what these two things added together is equal to. So that's something absolutely beautiful here, that this abstract addition rule here in the picture corresponds to that beautiful intuitive joining together of the two arrows. Okay. In addition, scalar multiplication is beautiful because that just corresponds to scaling the vector up or scaling the vector down or flipping the vector the other way. Okay, so it is beautiful how we can associate to this abstract structure here an intuitive, visualizable meaning. Okay, so what we now want to do then is have a look at these subspaces of R3 using our intuition for this vector space R3 in terms of this three-dimensional picture here. Okay, right. So we will start off then with the zero subspace. That's always a good place to start because any subspace, we know the criterion, the third criterion of being a subspace says that you have to have the zero vector in. Okay, so we might as well start with the zero subspace because that's the most fundamental any subspace can be because it has to fundamentally have that element in. Okay, so in terms of our picture then, that zero subspace is just a point in this picture. Okay, it is just the origin here. That's what this corresponds to. So that's a little point on this great picture. So that's the first subspace. Now let's go up a stage. Okay, let's say we want to put in some new vector into this subset. Okay, that isn't the zero vector. Okay, so we start off by saying, okay, we have to put the zero vector in because that always has to be there if we're going to be a subspace. But now I want to put in some other vector. So I choose one other vector that's other than the zero vector which I want to put in. And let's say that vector is this one here. So here is my picture for what this new vector is. Okay, so I just put in one more vector that isn't the zero vector into this set. Now, the instant that I put that in, I'm going to get loads of other vectors having to be in here as well, because remember criterion 1 and criterion number 2, I'll get them back up. Okay, a subset must obey these two criteria if it's going to be a subspace. Okay, so it must be closed under addition, but we'll come back to that one. Let's firstly do this scalar multiplication one. It must be closed under scalar multiplication. So I must be able to multiply v by any real number. Okay, get a new vector, and that new vector must be in my subset. Okay, now we have an intuitive view of what scalar multiplication means. It zooms this arrow up without changing its direction, or it zooms it down, or it even flips it round and then might zoom it up the other direction. Okay, so if I let c vary over all real numbers, then c times v can actually give me any vector that lies along this line that is parallel to that orange vector here. Okay, so what should I colour that in? So here is this line that that orange vector is part of, basically. Okay, and by multiplying that orange vector by any real number, I can turn it into any one of the position vectors to any of the points on this line. Okay, so the instant that I put that vector v in, I also have to have all of the other vectors that are on this green line, basically. Okay, so all of those have to go in here as well. So what this subset now is looking like is that entire line's worth of vectors, basically. Okay, so that's closure under scalar multiplication. Now let's make sure then that this line of position vectors, that this line is actually closed under addition. Well, it will be closed under addition because remember what addition intuitively means. Addition means put the two vectors end to end. Now if you have two vectors on this line, let's have another one here. Okay, a smaller one. and this one can be in pink here. So here's a smaller vector that's also on that line in pink. If I'm going to add those two together, then I'm just going to put this pink one on the end of the orange one here, and of course I'll still end up with something that's on that line. So indeed this line of vectors will be closed under addition. Okay, so lines then in our three-dimensional grid, lines of vectors, they do obey the axioms, obey those three criteria to be a subspace, okay? And I should stress it's lines that go through the origin. They must have the zero vector in. So you can dream up any line that goes through the origin that you like. You can twist this line around in any direction that you like. All of those lines, if you take all of the vectors that are on those lines and stick those into a subset, that subset will be a subspace. So now we've characterized a whole bunch of subspaces of R3 there. All of these possible lines in all sorts of different directions, they are all subspaces of R3. Okay, now what we're going to do is go up a stage from lines, okay? What we're going to do is we're going to say, okay, we've got this subset which is a line of vectors, okay, and I'll just actually put a list here. So we've got the zero subspace here, which was a point. We've now gone up to lines, okay, and I must say lines that go through the origin, okay, I'll add that go through the origin. Okay, and now what we're going to do is we're going to extend this. So we're going to say, okay, we've got some line, we've got a subset which is a line. What if I don't want a subset that's a line? What if I want to go bigger than a line? Okay, so I've got my line here, but I want to add another vector in, a vector that's not on that line. So let me now put this other vector here. So here is a vector that is not on that line. Okay, it's not parallel with all the other vectors that are already in my subspace. Okay, now, the instant then that I put in that vector, I'm going to have to put in a whole bunch of other vectors, and it's our job now to figure out how many other vectors am I going to have to put in. Well, firstly, the same argument that I used previously holds again. If I've got this yellow vector here, I'm going to have all scalar multiples of that, because if that yellow vector is going to be in my subset, then by criterion number 2, all scalar multiples of that vector must also be in my subset. So I'm now going to have the entire line that goes through that yellow vector here as well. And what colour should I colour that in? I'll colour that in red here. So I'm going to have all of these vectors as well. But now, let's think about addition. Okay, we want it to be closed under addition as well. We want it to be the case that if I take any two vectors in my subset and add them together, I have to get another element in the subset. What if I took one of the vectors on this green line and added some vector on the red line? Because now I'm saying all the vectors on the red line have to be in the subset. So I need to question, if I've got some vector in the green line adding some vector in the red line, is that going to be in my subset? And the answer is at the moment, no. So I need to add them in. Okay, so let me just draw what I need to do here. Okay, so for instance, if we use this orange vector here, and I want to add some vector on the red line, indeed actually I could add any of the vectors on the red line, and they all now need to be in my subset. What does it mean to add any vector on the red line? Well, it means put it at the end of this orange vector here, and then the overall point that you get to once you've gone down the orange vector and then the second vector, that's the new point whose position vector you want to be in your subset. Okay, so what this effectively corresponds to doing is something like this. So here is me adding the yellow vector onto the orange vector. Okay, and I need that vector, the overall vector, to be in my subset. But I could have done this for any of the vectors on the red line. So what I can effectively do is draw a red line also at the end of that orange vector here. Okay, like so. And I need all of these vectors that are on that line to also be in my subset. Okay, but this argument goes further. It goes on for any of the vectors on the green line. So in fact, I need red lines that go through any of the vectors on the green lines. So what I'm going to do is end up drawing loads of these red lines for all of the vectors on the green lines. Okay, and what I'm going to end up with, I hope it's available from the picture, is I'm going to end up with a great big plane here. Okay, and I'm going to end up with a plane that actually contains the original orange vector and the original yellow vector. So I'm going to overall have the plane that contains both of those vectors. Okay, so now the next thing that we're going up to is planes. Okay, planes that again have to go through the origin. Okay, go through the origin. Okay, so what I want to just convince you then is that any plane that goes through the origin will indeed be a subspace. Okay, and it's really the subspace that you get by insisting that you want to have two vectors that are not parallel to one another in your subset. Okay, right. So why then is a plane that goes through the origin actually going to obey the three criteria? Okay, well, as soon as it goes through the origin, it will obey the third criterion, which says that the zero vector has to be an element of the subset. Okay, why is it going to obey scalar multiplication? Well, because if you have any vector on the plane, let's say an arbitrary vector here that's on that plane, and you scalar multiply it, okay, it will remain parallel to some line that's within the plane. Okay, so it will, I hope you can understand from your intuitive visualization of this, remain in the plane. Okay, so when you scalar multiply a vector, it will remain in the plane that it's already in. Okay, addition, why is it the case that if you add any two vectors that are in the plane, you get another vector? Well, hopefully that should be available from the picture as well, and your intuition about this. If we've got some other vector here that's in the plane, and we add that one onto this one that's in the plane, we will end up with another one that's in the plane. Okay, so when you add two vectors that are in a plane together, you'll end up with another vector in that plane. Okay, you can't ever end up going out of the plane, basically. So planes that go through the origin are also subspaces of R3. Okay, and indeed you can reorient this plane however you like. Okay, so you can imagine twisting this plane around all over the place, and those are all subspaces of R3. Okay, or at least the sets that contain all of those vectors that correspond to those points is a subspace of R3. And then finally, what happens if we want to go a step up from that? What happens if now that I've got a plane and I insist on putting a vector that isn't in the plane in? Okay, so how am I going to show this? Let's say I've got a vector like this, which isn't actually in the plane. Imagine that it's pointing up in a totally different direction. So here's the plane. This vector might be pointing up like that or something. Okay, so not in the plane, basically. Okay, well, now what do I need to do? Again, as the instant that I say that I want that vector in, I'm going to have all the vectors that are on the same line as that in as well. So all of these vectors on that line are going to have to be in my vector space. And in addition, I'm going to have to make sure that it's closed under addition. So what I'm going to have to do is say I need to make sure that all of the vectors that are in the plane that I already had, plus any of these vectors that are on the yellow line, are also going to be within the vector space. So overall, what I'm going to end up doing is going onto every single one of the vectors in this plane and saying I want it to be the case that all of those vectors plus any vector on this yellow line is in my subset. So what I'm effectively going to end up doing is putting these yellow lines everywhere on the plane, okay, everywhere through the plane, and hopefully you can see that what will end up happening is you'll end up spanning the entire space. Okay, it will end up just becoming an entire three-dimensional space. Okay, your subset will end up being all vectors in the three-dimensional space. Okay, so the final one then is the entire vector space itself, R3. Okay, and indeed those are all of the subspaces of R3 characterized. You can either have the point, which is the zero vector, or you can have a line going through the origin, okay, in any direction that you like, or you can have a plane going through the origin, again in any orientation you like, or the step up from that is the entire vector space itself for R3. Okay, so I hope that that intuitive example of using R3 gives you some intuition for the meaning of taking subspaces of vector spaces.